On behalf of the entire team at TypeDB, both here in the San Francisco Bay Area and across the Atlantic in London, England, I'd like to welcome you to today's talk, TypeDB, the Polymorphic Database. My name is Alvin Leung, and I lead community and growth at TypeDB, and I'm thrilled to be able to welcome you, our global audience, to this stream. Now, in our previous lecture, Why We Need a Polymorphic Database, we explored some of the challenges that software engineers eventually encounter when their applications interact with databases with a higher order of sophistication or complexity. Moreover, it's notable that these challenges, object mismatch, maintaining semantic integrity, and polymorphism in the database, are encountered regardless of whether you're using a relational document or graph store. Today's presentation is in many ways a response to the questions raised in that talk, and we're pleased to be able to present TypeDB's solution to those challenges that we've identified. So to that end, I'm happy to be able to call to the stage again Dr. James Whiteside, research engineer at Vatical, the originators of Type. Now, by way of introduction, Dr. James Whiteside is an engineer with a rich background in programming and solid-state physics. With over a decade in both academic and industrial research, James has developed a profound passion for data modeling and algorithm design. His quest for expressive data modeling methods led him to join us at Vatical, where he immediately connected with the vision behind TypeDB. As a member of the research team, James is working to define an entirely new paradigm of polymorphic databases and aims to carry the vision of TypeDB forward by showcasing the unique and expressive power of the data models that he builds. And before I call James to the stage, I just want to mention that we will be taking questions submitted from the chat at the end of the lecture. Having said that, I do encourage you to submit your questions as they arise, as we have members of the TypeDB community on the chat who may be able to answer them immediately. And with that, I'd now like to invite James to the stage.
Thank you, Alvin, and thank you to everyone who's come here today. Today we'll be covering the next lecture in our TypeDB Fundamentals series, TypeDB, the Polymorphic Database. In this lecture, we'll be covering the core features of TypeDB, its conceptual data model, its type-theoretic language, its strong type system, and its symbolic reasoning engine. So let's jump straight in with its conceptual model, which allows us to define polymorphic schemas. TypeDB implements the polymorphic entity relation attribute model, or PIRA model, which is an extension of Chen's ER model. In the PIRA model, we have three root types: entity, relation, and attribute. Entities are used to represent independent concepts, like a user in a file system, for instance. Relations are used to represent concepts that depend on other concepts, for instance, a login event for that user. Relations have one or more roles, which are used to represent those dependencies. Attributes represent literal values in a domain. So we could have, for instance, the string james@vatical.com, which is in the domain of emails, and all attributes have value types like string, integer, and boolean. Each of these three root types have different capabilities. So entities can own attributes and play roles in relations. They can also be subtypes and be abstract. Meanwhile, relations can also own attributes and play roles in other relations, and likewise can be subtyped and be abstract. Attributes, on the other hand, cannot own other attributes or play roles in relations. They can only be subtyped and be abstract. On the next slide, we're going to see how we use these root types to build up a data model. This is a PIRA diagram, similar to an ER diagram. We can see here our entity types represented with pink rectangles, our relation types represented by yellow diamonds, and our attribute types represented by blue ovals. If we actually fit a model to this diagram now, we can see how we can use this to model a simple file system. So we've got the user type, which owns email. We've got file, which owns path and is a subtype of resource. Email and path are both subtypes of an abstract ID. And we've got a resource ownership relation type in which users play the role of resource owner in order to own resources. Now, we can translate this diagram directly into TypeQL. It's quite a simple model and would be simple to represent in most databases. We can see here the syntax that we use. We use the sub keyword in TypeQL to define a new type. either from an existing root type, entity, relation, or attribute, or a type that we've previously created. So we can see halfway down that we define file sub resource to create a new type file that is a subtype of our existing resource type. You can also see how we use the abstract keyword to make types abstract. We use the relates keyword on resource ownership to create the roles, and we use the owns and plays keywords to indicate implementation of the interfaces in our model, particularly ownership of attributes and playing of roles in relations. Finally, at the bottom we can see that we've specified a value type for our ID attribute with the keyword value, in this case a string. But this model is pretty simple. Let's try something more complicated, something that's more realistic. We're going to build a PIRA model for a DAC file system. That stands for Discretionary Access Control. It's one of the main access control frameworks, and it has been commonly used for file systems for a very long time now. In a typical DAC file system, every resource has an owner, and the owner grants permissions on those resources to other users. Now, the data model we're going to be working through, along with all the code and all the queries featured in this lecture, can be found at typedb.com/lectures/typedb polymorphic database, where at the bottom of the description you will find a lecture materials section with a link to GitHub repo containing all the code. And let's dig into our model now. We're starting off with the entity types. We can see so far it's quite simple. We've got a user type with a subtype admin. We've got user group. We've got an access entity type, which represents the different accesses that can be performed on resources. Speaking of resources, we've got a resource abstract type with two subtypes, directory and file. And already we've hit our first polymorphic feature of this model, which is abstraction. In this case, it's very useful to be able to refer to all the different resource types by a single common supertype. And it's very common, as we just have been doing, to talk about resources in a file system without specifying what kind of resources those are. And that indicates that in order to naturally model this data domain, we need an abstract resource supertype for all of our resources. Now, with our entities in place, we're going to give them some attribute types. So here, for instance, we've given the user type ownership of email, an active status, password hash, and a created timestamp. And here again, we've touched on two polymorphic features of our data model. We've got inheritance polymorphism over here, with admin being a subtype of user. It's going to inherit the capabilities to own all four of these attribute types. Another feature we've got is interface polymorphism, where we can see that user, user group, and resource each independently implement ownership of the created timestamp attribute type, despite having no common supertypes. Now, finally, we're going to introduce two abstract attribute types. Event timestamp, which is going to be the supertype of created timestamp and modified timestamp, and ID, which is the supertype of email, name, and path. And these are particularly important to the way we query our data and talk about the data domain. Particularly, ID is owned either directly or by inheritance by every entity type in the system. So every entity type owns an ID, and that's going to be a very useful feature. Now, with entities and attributes defined, we're going to move on to relations and the attributes they have. To begin with, we've got these four binary relations here. Group ownership, which allows admins to own user groups. Group membership, which allows users to be members of user groups. Resource ownerships, which allow users to own resources. And directory memberships, which allow both files and directories to be members of other directories. And once again, we've got some polymorphic features going on. We've got inheritance polymorphism over here on the left, because our admin type is inheriting the capabilities of being a group member and a resource owner from its supertype user. And over here on the right, we've got interface polymorphism, because both file and directory independently implement the directory member role. What that means is that we can use the single directory membership to represent a file that's in a directory or a directory that's in another directory, which is how we naturally model this domain. Next, we're going to introduce two more relation types to our model. Here we have login event and permission. And login event we're going to look at first. It has a single role, subject. So unlike all of the other relations we've looked at so far, it is a unary relation. And this can be quite difficult to model in some databases. Even harder is our permission, which is a ternary relation, because it has three roles: subject, object, and access. So every permission will be between one subject, one object, and one access. And we can see, just like directory membership, how we can use this to represent different kinds of permissions within our system. So we could use it to represent a user having permission to a particular access on a user group. We could use it to represent a user having permission to access a resource. We could use it to represent a user group having permission to access a resource, or a user group having permission to access another. And that nearly completes our model, but we're going to introduce finally a little more abstraction. We're going to make our two ownership types and our two membership types subtypes of abstract ownership and membership types. And that once again is a very important distinction which we'll be able to leverage later on. Summarizing what we've seen in this model, we've used several polymorphic features: abstraction, inheritance polymorphism, interface polymorphism, and n-ary relations. And capturing all of these within a database is a significant engineering challenge. However, with TypeDB, we can do it quite elegantly. Here we have a partial TypeQL schema for our DAC file system. On this slide, we're looking at the entities and their attributes. We'll do relations in a minute. And we can see, using the same keywords we introduced earlier, we can see how easy it is to implement abstraction. We just give our resource type the abstract keyword, and then we create subtypes of it. We can also see how we implement inheritance polymorphism. In this case, admin is going to inherit the capabilities to own emails, password hashes, created timestamps, and active statuses from its supertype user. And finally, we can see interface polymorphism at play. On the right here, we have the created timestamp attribute, and on the left, we can see how user, user group, and resource each independently implement ownership of that attribute, even though they have no common supertype. Moving on, we can now define our relation types, and we can see here with the relates keyword that most of relations are binary. We can see here though this login event only has a single role, subject, so it's the unary relation, while permission has three roles: subject, object, and access, easily implementing our ternary relation. Finally, we've got the list of role players here. We don't have any relations playing roles in other relations in this model, but there's nothing stopping us from doing that. And particularly, we see here that interface polymorphism at play once again. We can see that file and directory both independently implement the ability to be directory members. So now we've seen how we can convert our conceptual Pira model to a TypeQL schema, we'll see what that actually does for our database. It allows us to ensure the semantic integrity of inserted data. Here we've got three queries that are going to insert some data. The first one creates a new user. We're going to label her with the variable name Rhonda, and then we're going to give her an email, an active status, a created timestamp, and a password hash. In the next one, we create an admin, Cedric, and we're going to give him, again, 4 attributes that we've defined. And then finally, in our last query, we're going to match the existing user Rhonda by her email address, and then we're going to insert a login event in which C is the subject. Now, how do we know this data is semantically correct? Well, we can compare it to our schema. We can see that our first query is valid because user does indeed own each of the attribute types. But we can see that the second query is also valid because in addition to user owning those attribute types, admin is a subtype of user, which means admin owns them as well. Finally, in our last query, we can see how Rhonda is playing the role of subject in a login event, and indeed our schema tells us that login event relates subject and user plays subject. What if we try to insert some semantically incorrect data? Well, we've got two such queries here. In this first one, we're inserting a new user, Omar, but instead of giving him an email address, we're giving him a path. We're also going to give him a success status. And in our second query here, we're inserting another user, Avon, and giving him an email address. We're creating a user group, researchers, and we're making him the owner of that group. Now, the first query is obviously nonsense, but the second query is a little bit more subtle. Here, everything seems to be okay, but actually, Avon cannot be the owner of the user group because only admins can be owners of user groups, and Avon is not an admin, he's a regular user. And TypeDB can detect both of these cases. In the first case, it's going to detect that success is not defined to be owned by user, and in the second one, it's going to detect that user does not play the role of group owner. So TypeDB is able to now enforce semantic integrity based on the schema we've defined. How that works, we'll be seeing a bit later on. But to summarize what the conceptual model lets us do, well, we can capture the polymorphism in our data domain. We can then directly implement it using a TypeQL schema. We don't have to normalize or reify our model in any way. It's directly implemented, so we don't get any object-model mismatch. And finally, we can then use that schema to validate inserted data against and ensure we maintain semantic integrity in our data. Now, on to the second of TypeDB's core features, the type-theoretic query language. And we're going to see in this section how that enables us to compose declarative polymorphic queries. There are 4 types of polymorphic queries we'll be looking at. We'll be looking at those that use inheritance polymorphism. We'll be looking at those that use interface polymorphism. We'll be looking at those that use parametric polymorphism. And then finally, we'll see how we can query the schema directly. Let's start off with a very simple example of inheritance polymorphism. In this query, we want to list the email and active status for each user. In our match clause, we are binding a variable user, and the only constraint that we're applying is that that user must be of the user type. And then in the fetch clause, we're then retrieving the email and active status for that user. Now, these are the results we'll get back from TypeDB, or rather it's a selection of results. All of the query results we're going to show here are going to show just a few of the results that we're interested in. If you do want to see the full list of results, as I said, you can find the code on the GitHub repo and give it a go yourself. Let's break down what we get for each of our 3 results. Each of these represents one of the users that's been found, and we can see we get back the type of the user in the type field, we get back the email in an email field, and we get back the active status as well, because these are the things we queried for. But if we look a bit closer, we can see actually that our first result isn't a user, they're an admin. This result has been generated because admin is a subtype of user. TypeDB has directly implemented the inheritance polymorphism we've built into our model, without us having to specify that we're looking for admins. Let's look at a more complicated example of inheritance polymorphism. In this example, we list the ID and event timestamps of every resource. We're matching all of our resources, and we're retrieving IDs and event timestamps for them in the fetch clause. However, all 3 types that we've specified, resource, ID, and event timestamp, are abstract. And so just like we leveraged inheritance polymorphism in the previous query, we'll have to do it again here. And if we look at two of the results we get back, we can see that we're getting back files and directories, which are subtypes of resources. We're getting back paths, which is a subtype of ID. And we're getting back both created timestamps and modified timestamps, which are subtypes of event timestamp. And once again, we haven't actually needed to specify all of these types in our query. We just specified the abstract types that we were looking for, and TypeDB resolved them to their concrete subtypes. Let's move on to interface polymorphism. In this example, we want to list the ID and created timestamps of everything in our file system that was at some point created. And immediately, you'll notice that in our match clause, we do not specify the type of our variable x. We only specify that it has to have a created timestamp. So unlike in the previous query, where we were constraining our variable directly by its type, here we're constraining it by one of its interfaces, in this case, ownership of an attribute. Then, in the fetch clause, we retrieve the ID and the timestamp. Here are the results. In these results, we can see that we've returned several different types. So we've returned file, user, and user group because all of them own created timestamps. Let's look at a different example. In this example, we want to list the ID and owner ID of every resource. Once again, we've created two variables, resource and owner, without explicitly specifying their types. The only thing that we can tell is that those types have to play the role of resource and resource owner in a resource ownership. This is the result we get, and we can see we have two results here, and each result has two fields, owner and resource, containing the ID and type. And if we look at the resources retrieved, we can see that we've retrieved directories and files, because both of them play resource in resource ownership. And for the owners, we've retrieved user groups and admins, because both of them play the role of resource owner. We've also got a little bit of inheritance polymorphism going on here, because of course admin doesn't directly play resource owner, it's the supertype user that plays resource owner. And in fact, many queries that we'll write do have mixed elements of different forms of polymorphism in them. If we look at the full possible list of return types, we can see that files and directories can all be owned by users, admins, and user groups. Comparing that to our query though, we haven't specified any of these types anywhere. We've just specified that we want a data instance that plays the role of resource and a data instance that plays the role of resource owner, and then we want to retrieve their IDs. Bear this table in mind, because in the next section we'll dig a bit deeper into it and see how it works. Next, we'll look at querying with parametric polymorphism. In this query, we want to list the type and ID of everything that has a multi-valued attribute. We're going to break it down because this one's a bit more complicated. We are declaring a variable x, and we're saying that that data instance x has to have an attribute 1 and an attribute 2. Both of those attributes have to be of the same type, and attribute 1 is not the same instance as attribute 2. So they are in fact two different attributes. Otherwise, this would be trivially solved by matching the same attributes twice. And we can see here that the type of attribute 1 and 2 has been variabilized. We've variabilized it to attribute type. What this means is that rather than supplying the name of the type, we can actually now return it as data. If we look at the match clause as a whole though, we can see there are no explicit types whatsoever. So this match clause is independent of the schema. This is a common feature of all parametric queries. We could run a query featuring this match clause against any database, and it would always return a list of multi-valued attributes. In the fetch clause, we have then specified the ID type, but that is because in our query we are asking for ID, so that is simply unavoidable. If we then examine the results of this query, we can see we've successfully generated results of all kinds of different types. But particularly what stands out is that the attribute type that has been returned in each case is modified timestamp, because at this point in our data, modified timestamp is the only multi-valued attribute. This strategy of variabilizing types can be applied in other ways as well, particularly in querying the schema. In this query, we want to list the attribute types that files can have. Whereas before we were querying data instances, now we're querying only types in the schema. The keywords that we use in our match pattern are the same keywords we use to define our schema. In this case, the keyword owns. And if we run this query, we'll get back the 3 attribute types that file owns. We can see we've got back modified timestamp, path, and created timestamp. That here has leveraged inheritance polymorphism as well, because both modified timestamp and created timestamp are inherited from the supertype resource. Let's take a look at one more example of a polymorphic query. In this example, we want to list the concrete types that can play roles in ownerships. And once again, we see that we use our schema keywords to build up our pattern. First of all, we declare a variable ownership type, which is a subtype of ownership. We then bind roles that ownership type relates. Then finally, types that play that role. And we specify that the players can't be abstract. We then fetch the role and the player. And if we see our results here, we can see exactly what we've returned. We can see that user group plays the role of group in a group ownership, admin plays the role of group owner, file plays the role of resource, and admin plays the role of resource owner. We've returned 2 implementations of roles in group ownership and 2 implementations of roles in resource ownership, because they're both subtypes of ownership. Now, what benefits do these declarative polymorphic queries grant us other than really simple, really readable queries? Well, we can use them to extend the schema. Let's return to our data model, and we're going to define a few new types. So we've got some existing types here, and now on top of them, we're going to define some new types. A new subtype of resource, repository. Repositories are going to own names. Then we define a commit relation, which relates a repository to a user that plays the role of author, and commits also have created timestamps and own a new attribute, hash, which is a subtype of ID. We've got 2 important takeaways from this model. First of all, resource has a new subtype. And the second one is that created timestamp has a new owner. And what this means is that this inheritance polymorphism and interface polymorphism will affect the queries we've already written. So if we return to one of our queries from before, where we want to list the ID and event timestamps of every resource, repositories are resources too. So if we rerun this query, after extending our data model and putting some new data in, we'll see that among our results, repositories are now returned as well. Similarly, if we want to list the ID and created timestamps of everything that was created, which was one of our interface polymorphism queries from earlier, we'll see now that among our results, we now get repositories and commits back as well, because both of them own created timestamps, repository via its supertype resource. Now we can see quite clearly the value of the type-theoretic language. Using type variabilization, we can actually write declarative polymorphic queries that are easy to read and maintain. And the results of those polymorphic queries extend when the schema is extended, because they don't have any context from the data model hard-coded into them. But how is it that TypeDB is able to resolve these declarative queries? Well, that's because of the strong type system. And that also performs the semantic validation we encountered earlier. In this section, we're going to see how the type system works by examining type inference and semantic validation. Let's take this query, for example, from earlier. List the ID and event timestamps of every resource. We know that it has to return 3 variables: the resource, the ID of the resource, and the event timestamp of the resource, which means that it has three return types: the type of resource, the type of resource ID, and the type of resource event timestamp. It's important to note that this type function that we've created is purely illustrative and isn't actually a TypeQL function. It's going to help us with this explanation of type inference though. To begin type inference, we're going to need to construct a set of return types. And because ID and event timestamp both depend on resource, we'll start there. Examining our query, we can immediately see that our resource variable is of type resource, because we've directly specified it with the is_a keyword. So we know that resource is a valid return type. Now we can turn to our schema for more context. We can see that file is a subtype of resource, and so is directory and repository. And what this means is that these are also valid return types. If you'll recall, resource itself is abstract. That means that it's impossible to instantiate and so couldn't possibly be a return type of this query. And from there, we've now completed type inference for the resource variable. These are the possible return types. Let's see now how we use this to determine the return types for resource ID. We've denoted here, using Java generic notation, that the type of resource ID is dependent on the type of resource. We'll see exactly what that means in a moment. Let's begin with type inference. We know that the type of ID has to be ID, because it's quite literally specified there. But then, of course, we have four subtypes of ID: email, name, path, and hash in our schema. So those could also be possible return types. Finally, ID itself is abstract, so once again, it can't be returned. And this now gives us the possible types for resource ID. Now, we're going to start substituting in the values of type resource to see how they affect the set of return types. Let's begin with file. If we look to our schema, we see that file owns path, but it doesn't own any of the others. Therefore, the set of return types is reduced to just path when the resource is a file. Similarly, looking at the schema, we can tell that the return type of resource ID must be path if the type of resource is a directory, and when the type of resource is a repository, then the type of the ID must be a name. What we've established here is a dependency between the types of resource and the types of resource ID. And so what we're going to do, we're going to denote those dependencies using these arrows here. So you see that if we have a directory or a file, we have to get back a path for the ID, and if we have a repository, we get back a name. But email and hash cannot be returned. So in fact, they are not possible return types. We're now going to use the same process to infer return types for event timestamps. And it's getting a bit busy here, so we're going to introduce a little abbreviation. We're going to remove the generic notation, because we know that if we have a variable x and we're fetching an attribute y of that variable, then it obviously depends on the type of that variable. So we're going to remove the generic notation and we're going to rely on arrows to indicate the dependencies. Let's begin. We know that it must be of type event timestamp, because that's what we're fetching. And we see from the context in our schema that created timestamp, modified timestamp, and login timestamp are all subtypes of event timestamp, which means they could be returned as well. As before, we see the event timestamp is abstract. Now we start building dependencies to the type of resource. So resource owns created timestamp, and directories, files, and repositories all inherit that capability from the parent type. So all of them can return a created timestamp. And we see that resource also owns modified timestamp, so we end up with the same. However, none of them own login timestamps, so they are removed from the set of possible return types. And this has completed type inference. We've now established the possible set of return types for each of our variables and the dependencies between them. Now, if we want to start enumerating the set of types, we select one type from each set, respecting the dependencies that we've established. And we enumerate them now into this table. We can see how files, directories, and repositories are all possible return types for resource. Each of them returns a single type for the ID and either a created timestamp or a modified timestamp. And this is roughly how TypeDB's type inference works. Obviously, it follows slightly different procedures internally and makes many optimizations that we haven't considered here, but at a rough theoretical level, that is what the database is doing. It's using the context we've provided in the schema along with the structure of the query to infer the return types. Once it's inferred this list of possible return types, it then starts looking for data of those types. Let's try another example. We're going back to our query from earlier where we list the ID and owner ID of every resource, and we can see this query returns 4 variables, and so the query must have 4 return types. Let's once again begin type inference. First of all, we want to get the type of resource. Now, unlike before, where we directly specified the type using the is a keyword, here we haven't specified the type of resource, so we'll have to infer it. If we look to our schema, then we can see that resource plays the role of resource in a resource ownership, and so that is the possible return type. Once again, we could also get back files, directories, and repositories because they're subtypes, and resource itself can't be returned because it's abstract. Then we try and infer the type of resource ID, and we see we're in a very similar situation to before. In fact, this is identical to the previous query. So we're going to jump straight to the solution, where we're returning back paths and names dependent on the resource type. Next, let's look at the type of owner. So we know, once again, based on our query, that whatever the type of owner is, it must play the role of resource owner. We have 2 types in our schema that can do that, user and user group. And obviously, we are also going to be able to return admins because they're subtypes of users. Now with the possible types of owner inferred, we can now go and infer the ID of the owner. We know once again that we start from the type ID. We then can go to the 4 concrete subtypes based on the context of the schema, and then based on the ownerships in the schema, user and admin, which both own email, and user group, which owns name, we can establish the dependencies and then delete the types hash and path, which we don't need. Now there is one more step. We haven't established a dependency between our 2 types on the left and the 2 types on the right. And in fact, we could have any of those owner types owning any of those resource types. So what we do is we take the Cartesian product here. And now if we enumerate all of these types, we'll see a bit clearer what's going on here. We can see that we have the 3 resource types, file, directory, and repository, which can all be owned by user, admin, or user group, and for each one we return the appropriate ID. And what we can do now, we can compare this table to the one we had earlier for the same query, and we can see the effect that defining repository as a new type has had. We've defined 3 new possible sets of return types for this query. This shows us how we can extend our schemas by relying on type inference to continue to infer the correct set of return types based on the context of the schema. But how can TypeDB use this to identify if a query is semantically correct or not? Now we're going to look at semantic validation, and this process can be applied both to insert queries and to read queries. In this case, we're going to look at how it applies to 2 read queries. In this one, we want to list the ID of every permission and its role players. We begin by inferring the type of permission, and we've specified it. It can only be permission, and permission doesn't have any subtypes. Now we're going to skip subject, object, and access for a moment because they don't matter. We're going to go straight to inferring the type of permission ID. And we can see it's of type ID. Once again, we reach the 4 concrete subtypes, email, path, hash, and name, but now we run into a problem. Permission is not defined to own any of these types. So in fact, none of these types can be returned. And the set of return types for permission ID becomes empty. Because each result of our query must include every variable once, and exactly once, it is no longer possible to construct a result for this query because we can have no results for the particular variable permission ID. Because we can have no results, TypeDB throws an error. TypeDB has successfully identified that the projection from our permission variable to the attribute type ID is illegal because the variable permission could be of type permission, in fact it's the only type it can be, which doesn't own the attribute type ID or any of its subtypes. Here TypeDB has used type inference to perform semantic validation by identifying that there are no possible return types for this query and thus no possible results. Let's have a look at another query. That previous example was simply badly formed. Permissions don't have IDs in our schema, and it wasn't ever possible for it to return something. But here, we've just made a simple mistake. We want to list the login timestamps of every group owner. However, we've used the wrong variable on the second line of the query. On the first line, we state that we have a variable group that represents a group in a group ownership, and we have the variable owner that represents its owner. In our second line, we should be binding login events in which the owner is a role player, but we've accidentally put the wrong variable there. We've put in group. Let's see how TypeDB deals with this. First of all, we infer the type of group to be user group because while it's not explicitly stated, we know that the return type must play the role of group in a group ownership. And that's what we get from the first line. We then look at the second line, and we can see that the variable group must play the role of subject in a login event, and the only type that does that is user. We can, of course, now add in admin to our return types as a subtype of user. Now what we have to do is we have to take the intersection of these two sets. Because the constraints on the first line and the second line have to be applied to the variable group simultaneously, the only types that can be returned are the types that occur in both of these sets. And here's where we run into our problem. There are no types in the intersection, which means there are no valid return types for group. And TypeDB can now throw an error. It says that it could not infer compatible types for the match pattern. We've seen here how semantic validation is applied to read queries to ensure that they are always correctly constructed. And this same process is similarly applied to insert queries, as we saw at the beginning when our badly formed data inserts were rejected by the database. These are the benefits provided by the strong type system, which performs type inference to resolve our queries against the schema and identify the sets of possible return types. If no return types are found, then the query is deemed to be semantically invalid, which then throws an error. Now, we're going to look at a secondary benefit of the strong type system, but one of TypeDB's most powerful features. We'll be looking at symbolic reasoning. Now, symbolic reasoning is based on rules, and we're going to look at how we can define some rules for our DAC file system. We're going to look first of all at how we can define a simple rule, and then look at more complex cases, rule branching, rule chaining, and rule recursion. Let's start here with a query. We want to list the most recent modified timestamp for each resource. And we can see here that we're matching a variable resource of type resource and a variable t of type modified timestamp. We're then specifying an additional constraint that the resource can't have a second modified timestamp with a value greater than the first one. If that is the case, we then return the resource's ID and its most recent modified timestamp. We can see an example of a result here. But this is pretty cumbersome to deal with. Consider, for instance, if we wanted to compare the most recent modified timestamp of two resources. We'd now need each of these 5 lines twice, so it would become a 10-line query, despite being quite a simple comparison. Here is where we can use symbolic reasoning to improve this query. We're going to define, first of all, a new type, last modified, which is an attribute with a datetime value, and it's owned by resource. And then we're going to define a rule, resource last modified. Rules are defined as part of the schema, and they have two clauses: a when clause, which specifies the condition for the rule, and then clause, which specifies the conclusion of the rule. And whenever the condition is satisfied, the conclusion will be triggered. To begin with, we're going to take our original query pattern and we're going to substitute it into the condition of our rule. We're then, on the next line, going to copy the value of the most recent timestamp t to a value variable represented by that question mark. That just holds the value for us without a type. Then, in the conclusion of the rule, we're going to create a new last modified attribute for that resource, which has a value equal to the one we copied. And now we can take the line of the conclusion and substitute it back into the query, replacing the original pattern. This query is now significantly more readable. We can tell exactly what it's doing compared to the first one that we had to work through, and it will generate exactly the same results. If we look at our two queries side by side and the result for the first one, if we run the second one, the only thing that's going to change is the type of the attribute which is returned. It's changed from modified timestamp to last modified. And in this way, we can use rules to simplify our queries. Let's look at another example. So we're going to stick with the same query now, and we have this rule we've defined. However, there is a problem with this. If there are no instances of modified timestamp, then no last modified instance will be generated. Logically, we know what to do here. We have to copy the value of the created timestamp, which would be the last time it was modified. And we can do this by taking advantage of rule branching. We're going to write another rule here, which does exactly that. It copies the value of the created timestamp from the resource and creates a last modified attribute. And what we see is that these two rules have conditions that are mutually exclusive. The first rule specifies that it has to have a modified timestamp. The second rule specifies that it doesn't have a modified timestamp. So in this case, only one of these rules will be triggered for each resource. We can represent that logic here with a little flowchart. So we've got three branches here. In this first branch, when the query is executed, TypeDB searches for instances of last modified on disk and returns them. In the second branch, we trigger the rule resource last modified. We check if there are instances of modified timestamps on the repository, and if there are, we copy the value of the most recent one to an instance of last modified, and then we return that. In the third branch, we follow the other rule, implicit resource last modified. We first check if there are instances of modified timestamp on the repository, and if there aren't, then we copy the value of the created timestamp to a new instance of last modified. And TypeDB executes the three branches of this flowchart simultaneously and return instances of last modified found by these three methods in parallel. The results will be returned in a lazy stream. Now, let's extend our rules a bit further. We're going to go back to our original query, but now we're going to modify it slightly. Instead of the most recent modified timestamp for each resource, we're going to ask for the most recent modified timestamp for each repository. Let's recall our data model. We had repository as a subtype of resource, which owns created timestamp and modified timestamp, and now the inferred attribute last modified as well. But we also have commits, which own created timestamps. Now, logically, it makes sense that whenever we have a commit, the repository has been modified. So now the logic of generating the last modified timestamp for the repository has become pretty complicated, because now we've got to consider timestamps from three separate sources and find the most recent one. That would be the case with rule branching. but here we can take advantage of rule chaining instead. We're going to write this rule here, which generates new modified timestamps on the repository with values equal to the created timestamp of the repository's commits. If we compare this rule to the previous ones we defined, we can see that the structure of the conclusion of the new rule matches the condition of our previous rule, and it is the same for the other rule we defined. And what this means is that these rules can chain into each other. One of them can trigger the other. Let's return to our flowchart and work through it again. To begin with, we're going to simplify it a little bit. We know that our two existing branches of reasoning are mutually exclusive, and we're using the same condition in each one, so we're just going to combine them into a single branch there. Now, first of all, TypeDB is going to try searching for last modified instances on disk and start returning them. In parallel, it's going to trigger the two rules and start reasoning. However, as soon as it starts looking for last modified timestamps to satisfy the condition of those rules, it's going to hit the conclusion of our new rule. And so our rules will chain into each other. Before it finishes executing the first two rules, it's going to execute the new rule and generate new modified timestamps with values equal to the created timestamps of the commits. Only when it's finished doing that will it then return to executing our two existing rules and finish returning the instances of last modified. And as long as we don't have any instances of last modified on disk, this can only return one instance of last modified because our two rules are still mutually exclusive. Here we've seen how rule branching and chaining can be used to create complex logic that matches the domain logic of the data we're trying to model. And now we're going to look at one more special case of rule chaining, which is rule recursion. And for this, we're going to need a different query to work with. In this query, we want to list the directories that the type theory paper is in. If we run this query now, we're only going to get one result, the directory Vatical Research Papers. We know that we should be getting two other results. We should be getting Vatical Research and Vatical as well. In fact, we can even query to make sure the data is in our database. If we query for the directories that papers is in, we get back research as a result. If we query for the directories that research is in, we get back Vatical as a result. So we know the data is there. TypeDB just needs to leverage it in the right way. And what we'll do is we'll write this rule here. Wherever we have a directory 1 with a member directory 2, and that directory 2 has another member X, then X is also a member of directory 1. And we're going to create an implicit directory membership relation between X and directory 1. You'll notice here as well that X hasn't had its type defined, so it could be any type that plays the role of directory member, currently either file or directory. And that's going to allow this rule to apply recursively, particularly because the condition of this rule matches its own conclusion, which means it can chain onto itself. If we return to our query now with the rule defined and rerun it, we'll see we correctly return the two other directories that are parents of the type theory file. So to summarize what we've learned about symbolic reasoning, we can integrate domain logic directly into our database with rules. And we can create extremely complex behavior from rules that are individually simple. Symbolic reasoning has many more advantages in data engineering, but that will be the topic of a future lecture. Indeed, it's a whole other can of worms. In this lecture, we've explored TypeDB's core features, and we've seen how each of them provides us with a distinct advantage in data engineering over non-polymorphic databases. The conceptual model allows us to completely eliminate object model mismatch from our databases. The type-theoretic language allows us to compose declarative polymorphic queries that extend their own results when the schema is extended. Our strong type system allows us to guarantee semantic integrity of inserted data and queries we run against it, and symbolic reasoning gives us integrated application logic, which allows us to maintain internal consistency within our database. And these are just some of the features of TypeDB, the world's first polymorphic database. There are many other features that you can find on our features page, or you can find out more about TypeDB in our other lectures. On January the 9th, you can watch my colleague Christoph talk about the polymorphic data model of TypeDB. You can also watch replays of our previous lectures, why we need a polymorphic database, where I talk about the problems with existing database paradigms, and type theory as the unifying foundation of modern databases by Christoph, where he talks about the theory that has gone into developing TypeDB.
For next steps, in case you're more interested in TypeDB, there is a learning center at typedb.com/learn where there's a variety of resources that you can attend to just learn more of the language, some of the philosophy behind it. There's also links to lectures as well too, like this one and some of the other ones. So I encourage you to check that out. It's our learning center to get to go to TypeDB. And then if you're interested in actually experiencing and using TypeDB, there is you can go download it yourself at typedb.com/deploy, or I'm just happy to announce that TypeDB Cloud, our hosted offering, is now officially available. This is something we have been talking about for a couple weeks now. This is, and you can go to cloud.typedb.com to sign up and basically run a version of TypeDB for yourself without having to download servers and install and deal with all types of things. Thank you so very much for your time. We also encourage you to join our Discord community. And with that, I'd like to bring this presentation to a close. Thank you.
Thank you, everyone, for coming. See you next time.